to continue chapter 18. We should be able to get through this on Friday. Finish up this chapter. I've got quite a few examples that I've posted in. They're sample problems to do off of old exams. Probably Monday, we'll spend all day Monday covering what we can cover in chromatography, and then the exam Wednesday. So that's kind of where we're looking at. I don't think I've posted the videos for the chromatography, but maybe over the weekend, try to watch a couple of those. Okay, so we're going to try this again, see how I can hold up. And I have been to the doctor. It's not the flu. That's the good thing about it. So we're talking about electromagnetic radiation and ways that it moves. And we said there are two characteristics that we think about, and they're interrelated that we describe it with, and those are frequency and wavelength. And those two things are related by the speed of light. So C equals 3.0 times 10 to the 8th. That's a typo. I missed that. Times 10 to the 8th meters per second. If you want it to centimeters per second, it's going to be times 10 to the 10th. And then that's how we describe the wave model. As things permeate through space. If we want to think about it in the photon model, we have to look at it as a discrete bundle of energy permeating through space. So with each photon, the energy of the photon is equal to h nu, where h is Planck's constant, and nu is the frequency that we just described above. So if we have wavelength instead, we can use this formula rearranged for wavelength and resubstitute that in. It becomes Planck's constant times the speed of light divided by the wavelength. Thing I'll tell you when you do this, if you use the wavelength, make sure units of wavelength and C, speed of light, cancel out. Because a lot of times we describe our wavelength. I have that turned off. Life used to be good when telemarketers couldn't get cell phone numbers. Usually you describe wavelength in something like nanometers or micrometers or something other than meters, but you got to get your units to cancel out. A lot of times we'll do an energy conversion to talk about energies associated with things similar to bond energy. So we want to know, instead of an individual photon event, we would like to know how much energy that is in a mole photons. So we'll describe it in something like kilojoules per mole. So if you remember from organic, what's a single bond energy? Carbon-carbon single bond. Anybody remember those numbers? Okay, they're a little bit less than 500. 500 is a good round number. Double bonds about 1,000. Triple bonds about 1,500. Not an hour. When you talk about bond energies.
Yeah,
it's the enthalpy, the reaction.
Mass spec, is that what you're talking about?
Nope.
No?
Nope. This, I'm sure somewhere in organic stuff it was when it talked about bond energies and bond lengths and bond strengths. And he talked about the different ones.
That graph that if the bond gets stretched too much, the energy goes down or up, but if it switches
to the point that it breaks, yeah. Right. But we can start looking at, is there enough energy in light to break a bond? Okay, so anything that has an energy of the light that starts to exceed 500 kilojoules per mole, it's what we call ionizing radiation. So that's the point where that radiation can cause damage to chemical entities, including human tissue. Now, power is another term that we use occasionally, but it's just a measure of the flux of photons. So power is nothing more than energy over unit time. We usually describe that in watts. Now, sometimes we want to describe luminescence power, and we measure that when we did our experiment with the Spec 20 last week. What we actually measured was percent T, and that was a measurement of power, with light transmitted through the sample, what the power of that light was versus that of the blank. Okay, so just first a application of the conversion of units. So last year's exam, calculate the wavelength in centimeters of a C13 NMR signal at 22.523 megahertz. That happens to be where carbon resonates on our NMR. That's the reason I pulled that number out of the air. And then I gave you the speed of light. Okay, so we know our formula says that speed of light is equal to frequency times the wavelength. And I've got the frequency, I've got the speed of light. What I'm looking for is what's the wavelength. So lambda equals speed of light divided by the frequency. The speed of light is 3.0 times 10 to the 8th meters per second. The frequency is 22.523. Instead of putting megahertz, I'm just going to write it as 10 to the 6th. That's what a mega is. And a hertz, what's the units of a hertz? Who remembers that?
Per second.
Inverse seconds. So I'm going to put inverse seconds so I can see my units cancel out. And then the other thing I wanted to know is not as what's the wavelength in meters, I wanted to know in centimeters. So I'm going to go ahead and do another conversion that says in 1 meter, or 100 centimeters. So meters cancel out, inverse seconds cancel out, I'm left with centimeters. That's what I'm looking for in the problem, so it's just a little dimensional analysis problem. Thirteen 1,332 centimeters. Actually, we don't know that many significant figures. Based on the speed of light value we have, we only know it's there, but it's around 1.3, that's around 13 meters. And that's a long wave. But radio waves really are stretched out. Okay? They're the lowest energy, they're the longest. Any other questions on that? Okay. So let's look at another one. The exam question a couple years ago, how many kilojoules per mole are captured by O2 when it absorbs ultraviolet radiation at 147 nanometers? And I gave you a list of equations down at the bottom. So I know lambda, make it the smallest ink size. I know lambda, and that's the only thing that I'm given here. So the equation that I'm going to use is calculate the energy of a photon, and I'm going to use this. The E of a photon is equal to h times the speed of light divided by lambda, and I can just start plugging in and cranking out. So the energy of a photon is equal to Planck's constant, 6.626 times 10 to the minus 34th joule times seconds. Okay, speed of light, 3.00 times 10 to the 8th meters per second. And then finally my wavelength, which is 147 nanometers. And I'm going to convert from nanometers into meters so that I can get my units to cancel out. All right, let's see what we've got for for units at this point. The 10 to the, or the nanometers would cancel out. The meters and the meters would cancel out. I've got seconds on bottom, seconds on top. I'm left with joules, and I'm looking for energy, so let's type it. Okay, so now it's just cranking it out. And I got 1.35 times 10 to the 18th, minus 18th, sorry, joules. Okay, but that's the energy associated with every photon. So that's joules per a photon. And what the question asks, how many kilojoules per mole are there? So how do we know, how do we go from a number of particles to the number of moles we have? Avogadro's number. Yep. So, and Avogadro's number is a count system, just like a dozen. It doesn't matter if we're talking about atoms, electrons, in this case photons, molecules. So there are Avogadro's number, 0.22 times 10 to the 23rd of photons per mole of photons. And then the last thing is it asks, what is it in kilojoules? So there are 10 to the third joules per 1 kilojoule. Set up the dimensional analysis. Joules and joules cancel out. Photons and photons cancel out. I've got kilojoules over moles. That's where I want to be. 0.35 e to the 18th plus. So Avogadro's number divided by 1,000. Okay, that's 813 kilojoules per mole. Okay, so ultraviolet light at 147 nanometers. Is it something we should be concerned about if it's that much energy? Yeah, because it's over that single bond energy. So that's one of the reasons that we have to be careful with our exposure to ultraviolet light. Now, do you think it's enough energy to break the O2 bond? Why not?
Double bond.
It's a double bond, so it's a little bit above 1,000 or right at 1,000. So it's a little bit less than the energy required to break that bond. But you'll learn in, well, if you take an advanced organic class, you might learn something about some reactions occur or catalyzed by using different types of things like UV light to take something to an excited state. An excited state becomes more reactive, and it's an excited molecule that will then react and make a reaction go much, much quicker. Okay, so I tell you a number of joules here. So this is describing the photoelectric effect. So photoelectric effect is when light strikes a surface, it causes an electron to be ejected off. And it takes, there's a threshold wavelength associated with that with every node. Way back in Gen Chem 1, you talked about this in Chapter 8. So I want you to calculate what that minimum wavelength is. Knowing that the threshold energy is this 8.17 times 10 to the minus 19. Tell me how many nanometers the light has to be. Okay, for the good or bad of it, you can work on it together. Last time y'all worked one together, we didn't have a happy ending.
Cat wavelength by HC divided by pure. AC divided by energy. So, yeah, it's HC divided by energy wavelength, but it's going to be in meters, so you got to correct it. Yeah, super.
Oh, I just put it in. Thank you. All right, put it in. Only got 9 today. All right. So everybody says choice D.
Okay, I was like, I don't know. I went through.
Yeah, I had 9. I think that's everybody. That's missing the page and group. Okay, so does anybody want to see it work? Everybody got it.
You want to see it work it out?
Yeah.
Well, I like Dutch, that number, but I didn't get it right.
Okay.
Yeah, you got to multiply by 9. These answers.
That's what I meant. Okay, now I know.
Okay. Yeah, you had to go from,
Yeah.
when you solve it for lambda, lambda is going to be in meters. And then you have to take meters to nanometers. All right? All right. Old test questions. Okay. And then I went on the videos and I talked about the spectra. It's really worth your while to get this stuff down. What I suggest is the next 3 pages that you print these out full page. So you've got the PowerPoints. Go ahead and put these up, otherwise they're hard to read. But you need to know the regions of the spectra in terms of wavelength or frequency. You need to know what the quantum events are that are associated with those regions and what type of spectroscopies we do. So if we look at the relationships for the up-down questions that y'all love so much, the general relationships is the lower the wavelength means the higher the frequency. The higher the frequency, the higher the energy. So somewhere you're going to have an up-down arrow. What's the relationship questions? That's going to be answered with remembering that. And to give you an idea, if you look at an X-ray photon, which is not the most energetic, but it's up there, it's 10,000 times more energetic than that of a visible photon of light. So we have to limit ourselves to every time you get an X-ray, it's ionizing radiation, breaking bonds. You just want to control the amount of that you have to do. Usually you don't have a choice when you get an X-ray. I mean, it's a medical event driving that. Nobody go gets X-rays for the fun of it. Okay, another term that's used is one we use in organic all the time to describe infrared radiation. Those are wave numbers. And wave numbers are inverse centimeters. So it's a reciprocal wavelength. And it's given the symbol D bar. So wherever you see this, the D like frequency nu, new bar means inverse centimeters. And the reason that it's chosen to do that is that it's a linear scale with respect to energy. Wavelength's not a linear scale. Okay, so that's the reason the organic chemists have stuck to that one. So here's one of those tables that you should print out full page and learn. This has the frequencies and the regions that you need to know. The most energetic being on this side, so highest energy is on this side, are the gamma rays, then X-rays, then ultraviolet. In the middle of the visibles, the Roy G. Biv that we talked about in class and lab last week. Then going down to lower energy, infrared, microwaves, and then finally radios at the other extreme. All of those regions you need to know something about them. And then the other thing that you need to know is what type of quantum events occurring. Okay, so I'm going to start on the far side. So in radio waves, what's occurring over here is the spin of the nucleus. So it's either the excitation of a nucleus or an electron spin. And we use those in NMR, nuclear magnetic resonance, like you did in organic. And there's one we don't use as much called ESR, electron spin resonance. Okay, but it's used to study free radical species. Microwaves, we're looking at the rotation, three-dimensional rotation of molecules. Okay, we use microwaves almost daily as a household use to heat up water molecules. The way that they do is that it causes the water molecules to tumble, and as they get in motion, that's energy. So motion, kinetic energy, results in temperature, gets your food hot. Microwave doesn't work if there's no water in your sample. So if you've got a ceramic plate that doesn't have any water in it, you put it in the microwave, it doesn't get hot at all. If you've got a ceramic plate that's saturated with water, you learn quickly when you grab it in the microwave because it's burning your fingers. You learn pretty quick what you can put in the microwave, what you can't. Infrared deals with changes in either interatomic bond distances, either stretches or changes in bond angles. Okay, so they're either the stretches going in and out like a spring or changes in bond angles. So you've got three atoms here, and those two things are squeezing back and forth. That's the infrared region. All right. When you look at what's happening in the UV and Vis, it's the same event occurring. It's electronic excitations, in particular, they're the valence electrons. Right, the valence electrons are being excited from a lower state to a higher state. And if it doesn't matter if you want to think this is the HOMO LUMO is represented in this, like you learned in organic, or if you're going from a lower state to a higher state, like we taught in freshman chemistry, it's an excitation event that's occurring. What's happening in X-rays is you're now at high enough energy that you're starting to ionize and break bonds. In terms of the events that are occurring there, typically these are core electron excitations. You kick an electron out of one of these electrons, come in, it strikes something in the core, it kicks a core electron out, not a valence electron, and then you have a cascade of electrons falling down, and sometimes that causes a bond to break, sometimes it just causes an emission signal. And if you look at what's happening in gamma rays, you're changing the nucleus. So this is radioactive stuff. This is that's the stuff we don't want to be around. Okay, so here's the same table presenting something now associated a little bit differently. Here the scales are presented just slightly different. And the thing I'd tell you, choose to know it in wavelength or in frequency. Choose the scale that you want to learn and memorize to know where the regions are and be able to convert to the other. Now, if you look at the old test, I'll give you questions where what wavelength, what region is this? So given the wavelength or given a frequency, what region is this? We're going to have questions like that to address. this is similar type information. I just like the pictures in this one. I think they tell you a little bit more about what's going on. So this one, though, is oriented a little bit differently. This one has the lowest energy. It's flipped around compared to the other table. It's got the lowest energy on the left, so this is the longest wavelengths. And it's easier to read the wavelength scale on this one because everything's kind of broken out in a log base or a factor of 10 to 100. So what's happening is this is associated with the different types of spectroscopy. So this is the radio wave regions. You're talking about the spin of a nucleus, NMR, the spin of an electron spinning around, ESR, microwave, it's the change in orientation, the tumbling. Infrared, it's a change of configuration, change in nuclei distances and the vibrations, or change in bond angles. If you look at what's happening in the UV vis, it's the valence electrons being excited. In X-ray, it's core electrons being excited. And in gamma rays, you're changing the nuclear configuration, so you don't have the same substance that you started out. Okay, so somewhere you're going to have a couple questions for those tables. Yes?
What's going on in an MRI machine?
MRI basically does what NMR is. So MRI is fundamentally NMR looking at water molecules and done in a three-dimensional image. So one of the big things now that they're doing in MRI is there's something called fMRI, and it'll actually look at a shift for you and look at it in a three-dimensional object. So now you can just not look at soft tissue, which is typically what we use in MRI, our MRI for in water, to look at ligament damage or nerve damage or whatever it may be. Now you can actually start to trace where a particular compound is bioaccumulating. And if you know what type of compounds may be present in the cancer tumor, okay, you could go in and take a three-dimensional object of it to find exactly where that substance is. So right now that's a pretty cost prohibitive, that's a very expensive machine, and it's a very lengthy scan. Typically if a patient has it, a human patient has it done, the scan takes anywhere from 8 to 12 hours to do, just like the brain. So it's very, very slow to do a high-resolution three-dimensional grid, so typically they knock the patient out. So it's just not used commonly. In the future, it's probably will be one of the things that will be coming up.
Where do we hit ionizing radiation?
Okay, so the ionizing radiation is going to be everything to the right of X-rays. Okay, so whenever you're involved in these core electrons, that's ionizing. Okay, all right. Here's last year's exam question. So, which one of the following would represent a core electron configuration, a change in core electron configuration? X-rays, visible light, microwaves, radio waves. It's not a quick question.
Oh, okay.
It's just an example of last year's exam question.
X-ray.
It's X-rays. Yeah. All right. So let's look at another one. Oh, this one is a clicker question. Oh, that sucks.
Mm-hmm.
Okay. I didn't realize that. I just went and got a question off of last year's test. I didn't realize it was the second question. Oh, well. Sometimes you get a feeling.
Yeah, we had.
Oh, somebody else came in. Yeah, go ahead. It's doing it again. I'll have to delete the first one out. All right. So everybody go see. Golly, I hope it's C. Yeah, let's see. Okay. So whether you want to recreate this table on your cheat sheet, that's your option. I'm not giving it to you. Okay, so I'll give you Planck's constant. I'll give you the speed of light, but everything else is going to be Up to you to put on there. Okay. That's something different.
Have your slides?
No, not up here.
We're all in. 10, right? Yep. All right. Survey says. Okay. Everybody thinks it's one of two. It's either C or D. It's D. Okay. So if you're at so 100 gigahertz, or 1 times 10 to the 11th. If you look in the frequency range here, you're between these two. Okay, so if you're looking at what is that one, that's the, this is infrared, this is microwave. Your regions. All right. So there are basically a couple of different types of regions that we classify as optical. And optical simply means that you can manipulate the light with traditional lenses and mirrors. If you look and you shine the radio waves through a piece of glass, they'll either be transmitted through it or they won't be reflected. They'll be absorbed by the matter. So the things that we can deal with the optics are the UV region, the visible region, and the infrared. And I've defined what those regions are in terms of nanometers or wavelength. Just keep in mind that your transition from nanometers to micrometers is a factor of 1,000. So where the visible ends at 780, the infrared starts on at 0.78. So those regions all back up to one another. So whenever you have the capture of a photon of light, you go from a ground state to the excited state represented by M star, but things don't want to be in the excited state. They quickly give that photon of light off, and they can either give it off as heat. There are a couple of different mechanisms. We talk about those in instrumental analysis, but where you bounce off of each other, you have collisions. Another way that they emit that energy off is an emission event. All right, so they give off light, they glow, and that's luminescent spectroscopy. The key thing is the equation down at the bottom that says the total energy of an atom or molecule is equal to the energy electronic plus the energy vibrational plus the energy rotational. And the reason that's important because that tells us something about the shapes of the spectra that we're going to see for different substances.
Dr. Smith, I'm just curious. So how does like night vision devices, how do they convert infrared light to like visible light?
Well, most of them don't. Okay, so most of the ones will use and enhance the light that's there. Okay, that's your older starlight type night vision, and they just do light amplification. Is all they do. The problem with those, if you expose them to high light, you blow up the circuitry. You know, the more expensive ones, there are some today that use an infrared illuminator. So you have to have an infrared, basically, flashlight on it, and it will shine out and it reflects the infrared back, and it's an infrared camera that simply sees it. Those are a couple $100 now, going up to. I mean, that's the low end ATN ones. If you want the high quality stuff for thermal imaging, they're passive infrared. So what it does is it sees thermal energy in a way so our eyes can't see it, but you can build electronic sensors that can. And there are some animals in nature that see in the infrared. An example of it is a rattlesnake. A rattlesnake and all the viper family basically have two sets of eyes. They have a set of eyes, they're normal eyes that they blink with, that see the visible light, but underneath it they have a set of infrared sensors, and that's the reason they mainly hunt at night. They see in thermal images with the other set of eyes, and their brains does both of those. So today, I worked on a project with the Air Force, and one of the things we were looking at was to look at polymers that could absorb infrared light and would emit by doing photon stacking, because the energy is a lot less of a thermal photon in the infrared. You'd have to absorb maybe 10 or 15 thermal photons, and if that could trigger an event that would release a visible photon, you could basically put on a set of glasses that were nothing more than sunglasses, had this correct polymer in it, and you could see it in infrared. That's the way a Viper works. And there was a lot of we never accomplished that. But that was where that research project was working towards. It was a military application associated. Today, there's umpteen sets of night vision things that you can get. That you can actually get a thermal sensor that goes on the back of your iPhone. That's in your iPhone that you can put on there and you can scan and see if there's anybody around you in the dark. And they're a couple $100. So it's having a detector that's sensitive enough that low enough energy is all. Okay. All right. A lot of this I went over on the videos, and it's stuff that we talked about in the lab, but I just want to highlight some of it. So whenever we're doing spectroscopy and doing absorption events, we're looking at light going in at a certain wavelength. And we have an incident power, P0, that we use to measure with a blank. The light goes through the sample. Part of it's absorbed or not. And then we measure the amount of light that goes through. And transmittance is the ratio of P divided by P0. Okay, so if we think about what's happening in terms of the photons, you have an event that occurs where these quantum events, you go from one energy level to another. So each one of these jumps represents a different wavelength. So you have a unique wavelength. This represents a certain change in energy, which represents a certain wavelength, whatever lambda x is. Okay, and if I go to a different transition, this would be a different lambda. Okay, that's where we get uniquenesses. Every compound has different transitions that can occur. It has uniquenesses there. Now this table covers the visible light spectra, and keep in mind the color that we see is not the color that's absorbed. For example, if I choose the 500 to 502, the color that's absorbed is the green. The color that we observe is the purple in that. Okay, so we see the complementary color out of when we look at the color and things. And one of the things that some of you had asked about, that there's chalk in some of these cuvettes from the example last week. So one of the things that sometimes when we have more time, I would have students take a piece of chalk that had cut at an angle, and you could dial the different wavelengths in, and you'd look down on it and you could see what that color is exactly at that wavelength. And that's one thing that we can find out how we're different and unique. Some of you can see color all the way down to 400 nanometers. I can't. I'm off at 30. Some of you can see color all the way up to 750, see reds all the way up to 750. We all see things a little bit different. That's one experiment that you can do that allows us to see different things. Okay, so if we look at that concept of absorbance, we have an incident light coming in at some wavelength P0. It goes through the sample, it's absorbed, it gets P. Transmittance, as we said, was the ratio of P divided by P0. And from that, we can calculate absorbance by taking the log of the inverse of that, or the negative log of T. And where we have unique peaks in what we call spectra, a plot of wavelength versus absorbance, is due to the different energy transitions. So each one of these represents a different energy transition in a chemical entity. So if we think about the possibilities that percent T can be, it can be from 100 to 0. 100% transmittance means none of the light's captured. 0% T means that all of the light is captured. None makes it through. Okay? And hopefully you saw in lab that it was an inverse relationship to absorbance. And usually we think of the scale that goes from 0 to 2, but really, if it's at 100% T, truthfully, it's going to go to infinity. Okay? It's really not going to 2. And if we look at the relationship that's shown on the graph that's on this next page. So here's the absorbance and the percent T scale that we have. So once we get down to something that's below 5%, I mean, this number really, really starts to get large down here on this side. But you had something like this on your graph that had a spectra that looked somewhat similar to this. So here are the percent T, the absorbance, and then it plotted a log of that. So on this particular compound, it looks like the maximum percent T is about, let's see, what's that scale? So that's about 40, 520-ish, something like that. Okay. Different instruments can separate light out better. The instrument that you were using, the Spectronic 20, the 20 comes from, there's a 20 nanometer bandwidth. So it can only see 20 nanometers at a time window. It could never do the fine detail to be able to resolve this peak that's less than 10 nanometers wide. It would see that as a smooth hump. Right? So, but we have another instrument next door that we use in instrumental analysis that has a wavelength separation of 100 nanometers. So it could get in very, very fine detail how these things would separate or pull from one another. And of course, the main way that we utilize this is we convert samples into absorbance, and then we apply Beer's law, which says absorbance is equal to absorptivity times path length times concentration. And the units that you have of absorptivity are defined by whatever path length and concentration are. Because absorbance is unitless. So if you're in centimeters, path length, centimeters, that means the absorbance is inverse centimeters. Or the absorptivity is inverse centimeters. If concentration is molar, you're going to have units of inverse molar on the absorptivity. Right. Most common form of absorptivity we use is molar absorptivity, and we give that one the name epsilon, and it has units of inverse centimeters, inverse molar. That's with the concentration being given in molarity and path length in centimeters. So a key thing about it is, as long as I keep the wavelength fixed, that means the absorptivity is the same and the path length is the same, that I've got a linear relationship that exists. So these two terms, if I'm not changing the wavelength or changing the cuvette, those two things are constants. So now I have something that we can plot. Absorbance is equal to a constant times concentration plus an intercept. Theoretically, there shouldn't be an intercept, but reality of data is that sometimes there is. But we should have a linear relationship that exists between these things that we can define. That becomes our calibration curves. Right? So a key thing to realize is that absorptivity is dependent on the wavelength. So when I change the wavelength, what I'm essentially looking at is a different molar absorptivity. So when you ran your standards of permanganate to find out where to measure at, and you've got different percent T's at all the different points, what you were looking at were points of different molar absorptivity. Okay? So a spectra is simply a plot of the absorbance, or it could be the transmittance, versus wavelength. And the key thing, we use that to identify a substance. Now, our instrument gave us approved identification because it wasn't a high-resolution instrument, and we knew we were making permanganate. But I had something else that was there I could use to confirm that it was or wasn't. And I wouldn't have a high degree of confidence that it was It's just when you look at different instruments, you have much greater detail. Okay, the absorbance is directly proportional to the concentration. So if one goes up, the other one goes up. And if we look at the portion in the sample that absorbs light, if you have a given sample, not every component in that compound absorbs the light. The portion of the molecule that does absorb light is called the chromophore. Now, the value for the molar absorptivity varies a lot. If something doesn't absorb at all at a given wavelength, it's got a value of 0, and then it goes up from there depending on what the probability of photon capture is. For things like dyes, the molar absorptivity can have a value greater than 100,000. So organic dyes, like you use to give color to cotton clothing, there are literally milligrams of dye that are placed in 100 pounds of cotton fiber. And that just a small amount of dye absorbs into the surface of that, but the dye's color is so intense it gets colored in. Okay? That varies with the wavelength and the probability of photon capture. Okay, so we'll start this. I've got a series of 5 or 6 proton problems. We're certainly not going to get through all those, but we'll just start off. Okay, so find the absorbance in the percent T of a certain concentration of a substance that has a molar absorptivity that's given in a 2 centimeter cell. So it's just a try and get through problem. A number absorbance is equal to molar absorptivity times path length times concentration. And what do I have of those? I've got the molar absorptivity is 313 inverse molar, inverse centimeters, times the path length. It's a 2 centimeter cell. Okay. Times the concentration. So if I look at what happens to units, molarity cancels out, centimeters cancel out. I'm left with something that's unitless. Okay, 1.50. Okay, so if absorbance is 1.50, you tell me what T is. I think I did that right. Okay, move the 2 for it's a minus, it's a negative. Oh, I didn't lose my negative. There's 1.2%. So I took and subtracted this to the other side. Took the negative of both. That's what this is. So I moved the negative over. And to find out what the T was, I took the anti-log of both sides. that's it for today. We'll continue this. I've got a lot of more problems, example problems to work, but we'll finish the chapter up. About 15 slides left on Friday. Okay, be safe.